Hey guys, today is March 13th and I'm going to do another LeetCode Daily Challenge. So yesterday's question I wasn't able to do, but I learned quite a lot from it, so hopefully we could apply that to today. Oh, I feel like I've done maximum candies before. Oh no. Maybe there's another problem that has to do with candies that's similar. Let's see. Okay. You are given a zero index integer array candy. Each element in the array denotes a pile of candies of size candies at I. You can divide each pile into any number of subpiles, but you cannot merge two piles together. You are also given an integer k. You should allocate piles of candies to k children such that each child gets the same number of candies. Each child can be allocated candies from only one pile of candies, and some piles of candies may go unused. Return the maximum number of candies each child can get. Wait, what? I don't really understand. So here are the three piles. What's K? You should allocate piles of candies to 3 children, such that each child gets the same number of candies. Each child can be allocated candies from only one pile, and some piles of candies may go unused. I see. So since there's 3 children, let's just take the max of these. Return the max number of candies each child can get. So 5, right? Because this one would get 5. This child would get 5, even though there's 3 left. And then this one would get 5, and there'd be 1 left. So what is the explanation? We can divide candies 1 into 2 piles of size 5 and 3, and candies 2 into 2 piles 5 and 1. We now have 5 piles of candies of size 5, 5, 3, 5, and 1. We can allocate the 3 piles of size 5 to 3 children. Just reading it and knowing that we've been doing binary search recently, this feels like a binary search problem. That being said, I don't know what the approach would be right now. I feel like I would like more examples. I mean, this first example is interesting because, I mean, k is 3 and we already have 3 piles, so we just take the minimum of those 3, right? So we just take the minimum of this array, which will spit us 5, so that should be our answer. But I think maybe I just come up with my own test case, honestly. So what if k was 4? I think that would be helpful. So we have 5, 8, 6, right here. What if we want 4 piles? Maybe we have to do some greedy aspects. So the array, like, okay, so we know that there's 4 piles that we want, and we only have 3 piles to make subpiles from. So I don't see any case where we would want to just get like a small pile and and create an even smaller subpile, that wouldn't be efficient, right? Because the maximum number of candies each of these children can get is the minimum of this new pile, right? Is the minimum. You cannot merge two piles together, yeah. Okay, so I think what I would want to do is 586 is just to maybe sort it. Maybe sort it. 865. Where like the first, I don't know, like sort it in decreasing order. Like the first thing is just the max candies. And then maybe we can split this. So we can split this one. So it'll be 4, 4, 6, 5. And then let's just take again the minimum of these 4. And that's going to be 4. So our answer is 4. Like I don't know if I'm doing that right, so let me test that out. So K is 4. What does it return usually? Okay, returns an int. Return 0. Okay, it's expected 4. Yeah, that works. But I'm still a little bit confused on how I'm going to split. So we'll see. Maybe I could do just another example. 3, 5, 7, 2, 8 with a K of... Right, so... Oh, but what if it's a K of 4? If it's a K of 4, we only need to look at the... If we sort this, right, into 8, 7, 5, 3, 2, we only need to look at the first 4. And then just take the minimum of that. 3, 5, 7, 2, 8 with a K of 4 should be a 3. Wait, why is it a 4? Oh. Because we could split 8. Oh my gosh. We could split 8 into a 4, 4, then a 7, then a 5. And then we take the min of that, and then we got 4. I don't know. Damn, I really don't know. Damn. Yeah, I think I'm just rambling, which isn't good, but... Oh. Okay, example 2. We are given 2 and 5 with a K of 11. There are 11 children, but only 7 candies total. So it's impossible to ensure each child receives at least 1 candy. So do we need to sum up the... We need to sum the candies? And make sure that the sum of the candies is greater than or equal to K? Otherwise, we return 0. Okay. Okay. I kind of see a binary search approach, and it has to do with summing up all the candies. So I'm going to do this with the example that I wrote down here, and we're going to try something. 3, 5, 7, 2, 8. That is our original candies. And then let's have a K of 4. So right off the bat, it's kind of hard to know, right? Like before I was like, oh, let's just sort it and take the minimum of the first 4. But that doesn't work because we might be able to split. So actually, let's do a binary search way where what is the smallest, I guess, is 0, right? I don't know. Our smallest possible result is 0. But then let's go all the way, like if it was on a number line, it would be 0 all the way to the sum of the candies. So I just need to sum this up. I know that this is 10, this is 10, so that's 25. So sums to 25. Let me just double check that real quick. 10, 25. Okay. So then we'll do the middle. So maybe like 12 or something. And then see if we can make 4 piles of 12. 4 piles of 12. Okay, so we just take our original input, right? Yeah, we just take our original input. Let me see here. 4 piles of 12. Here's our original input. Can we do a 12 right here? Nope. Can we do 12 here? No, 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 no. Okay, so that's not going to work. So since this didn't work, we have to search to the left because our result is smaller. Like each child cannot get 12. So that means each child needs to get somewhere in here. So let's do that again. Let's do a binary search to find the middle. And this is the left, and now this is the right. Okay. In the middle would be 6. So can we do 4 piles of 6 this time, right? Can we do 4 piles of 6? No, no. Yes, we can make a pile of 6. No, and yes, we can make a pile of 6. But that does not equal 4. So we cannot do 6. So we have to keep going. Now this becomes right, or sorry, right should be 1 less than that, but who cares? And then I'll just put like a 3 here as the mid. So then let's say if we could do 3, yes, 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 yes. So that works. So then we should search to the right of 3. So let's just say we're searching 4. No, no, yes, yes. And then can this be pile of 4? Oh, yes, yes. And then we could actually split 8 into 2, right? It could be a pile of 4 and a pile of 4. Okay, so I think that's what we're gonna do. Wow. That's pretty cool. If it works, that's pretty cool. Binary search. So one important thing is that we know what bounds we're doing when we do binary search. It's not like we just binary search on an array, right? Because that's pretty easy. That's like obvious that it's this index and that's going to be our left and this is going to be our right pointer. In this case, it's what is our left. Let's just say it's 0. And what is our right? So 0 is our left and right is going to be the sum of the array. Sum of the Candies array. Okay, so what is the binary search part of this? Wait, let me think for 1 second. They want the maximum number of candies. So if something does work, that should be our result, right? So our result could be... Let me just bring some of Candies here. It will be tote Candies. Let the result be... I don't know, maybe tote Candies plus 1. While left is less than equal to right. We have to check, get mid, right? Mid is left plus right minus left divided by 2. Check if we can make k, which they give us k. We can make k piles of mid candies. Mid is the number of each pile. So let's just do if can make with the mid, then we know our result is going to be at least mid. Wait, the maximum number of candies? So if we're doing binary search and mid was, we were able to make those candies, then we should search to the right. Yeah, I think so, right? Res is mid, and then left is equal to mid plus 1. Otherwise, if this was not good, we have to go smaller. So we need to go to the left, which means right has to be mid minus 1, and it's not going to be part of our result. Okay, that's fine. I think so. I think this is okay for now. We'll see. It might be off by 1, or we might need to tweak it a bit, but I think that's okay. And then later we just return the result. And then might have to do a check if res equals tote candies. That means we never found a result. So we'll just return 0, right? Return 0. Okay, all that's good. Now I just need to create a function, can make. And it's going to return some sort of Boolean. It's going to have num candies. Okay, so this is the number of candies per pile, and so num candies represents the number of candies per pile. K, which is right here, is the number of piles we want to make. Okay. And then I think we just loop the candies, right? So for candy count in candy, for candy, I'll just do for candy in candies. Wait, so if we were given, like, if we wanted, if our num candies was like a 3, and we were currently on like a 5. We do 5 divided by 3. Yeah, to give us 1. So we need to do 5, which is candy, divided by integer division by 3, and 3 is the num candies in each pile. This will give us how many piles, right? So piles is 0. This will give us the piles. We just keep building that. Just need a order of operations. That's fine. Return piles. We want at least k, right? So return piles greater than equal to k. Return piles, is piles greater than or equal to k? If yes, then we can make. Should be true. Okay, that should be fine. Let me run that. Integer division or modulo by 0. Okay, so num candies is 0. It's because I'm putting a 0 right here. Let me think. Wait, what does it mean when the sum is... What does it mean number of candies? Represents the number of candies per pile. 1 candy per pile. I guess that could be a base case, not 0. Maybe we just start at 1. Yeah. Okay, everything else passed, but this one, let's see. Whoa, why is it outputting an 8? Okay, that's kind of strange. I'm wondering if I need some sort of base case. Or if res equals total candies plus 1. Because if basically if res becomes unchanged. Does that mean this? If not res, return 0? Let me see. Okay, it might be that. I'm just checking, like, if we never found a valid one, we should just return 0, right? Okay, let me submit this, see what happens. Awesome, yeah, nice. Cool. So yeah, I mean, problems like this are pretty cool, especially like those binary search problems. I wouldn't say I'm like super good at them, so something like this takes time, but this type of problem reminds me of, there's another LeetCode problem, Coco eating bananas. And this one, if you have time, you should check it out. It doesn't seem like a binary search type problem. Like just reading the stuff, it doesn't seem like that. But after doing this one, I kind of understand why we're using binary search. So yeah. Yeah, that was pretty cool. What is the time complexity? So it's like, okay, wait, it's like log n for sure, right? Log n, but what is n? N is the sum of the array. So it kind of depends. I don't know what that type of thing is called. But we're doing a log n, which is right here. And then what is can make? Can make just runs through the candies. So actually, what if I just did m is the sum of the candies and n is the length of the candies array. So it's going to be log m times n, or n log m. Awesome. Okay, that's it. And see you guys tomorrow.